Hello, and welcome back to another gentle journey through the mysteries of our world. Tonight we're embarking on something a little different, a slow, meandering exploration through the forgotten corridors of scientific history. If you're settling in for the evening, perhaps with a warm cup of tea, or simply seeking a quiet respite from the day's demands, you've come to the right place. What you're about to hear isn't just a collection of facts or dates, it's a tapestry of human curiosity, woven from threads of wonder that stretch back thousands of years. Some of these stories have been deliberately hidden, others accidentally lost, and still others dismissed as impossible until time proved them remarkably prescient. Before we begin this gentle odyssey through time and knowledge, I'd love to know, where in the world are you listening from tonight? And what draws you to these quiet mysteries that live in the spaces between what we know and what we've forgotten? If you find these explorations soothing, or if they spark something curious within you, I'd be deeply grateful for a gentle tap of the like button, or perhaps a subscription to join us on future journeys. These small gestures help this little corner of calm reach others who might need it. Now let's dim the lights of the modern world and step back through the centuries to a time when the boundary between science and magic was as thin as morning mist. Chapter 1. The Soft Hook of Ancient Whispers. Picture, if you will, a moonlit courtyard in ancient Baghdad, circa 850 CE. The air carries the scent of jasmine and parchment, and in a corner of the House of Wisdom, a figure hunches over calculations that won't be discovered by European scholars for another 3 centuries. This is just one of countless moments where knowledge bloomed in secret, was lost to time, or deliberately obscured by those who feared its implications. The history of science, you see, is not the neat, progressive narrative we often imagine, a straight line from ignorance to enlightenment. Instead, it resembles more a vast underground river system, with streams of knowledge appearing, disappearing, and resurfacing in unexpected places and times. Some discoveries were made by individuals whose names were erased from history, others were suppressed by institutions threatened by new ideas, and still others were simply forgotten, like books left on library shelves that no one thought to open again. Tonight, we're going to follow some of these hidden streams. We'll meet the anonymous women who made breakthrough observations in medieval monasteries, the Islamic scholars whose mathematical insights were later attributed to others, and the indigenous peoples whose sophisticated understanding of astronomy and medicine was dismissed as mere superstition until modern science rediscovered their wisdom. But this isn't a story of villains and victims, though there are certainly both in our tale. It's something more subtle, a meditation on how knowledge flows through time, sometimes above ground in the bright sunlight of recognition, sometimes beneath the surface, carried forward by whispered conversations and carefully guarded manuscripts. You might wonder why these stories matter now. In our age of global connectivity and instant information, the answer, perhaps, lies in what they reveal about the nature of discovery itself. Truth, it seems, has a curious way of emerging regardless of the obstacles placed before it. Like water finding its way through rock, scientific understanding has a patience that outlasts empires and ideologies. Consider for a moment the woman known only as Trotula in medieval medical texts, a name that may have represented not one person but an entire tradition of female medical practitioners whose knowledge was systematically appropriated and masculinized. Their understanding of anatomy, herbal medicine, and surgical procedures was remarkable for its time, yet their contributions were gradually attributed to male physicians, their names fading like ink in sunlight. Or think about the Antikythera mechanism, that extraordinary bronze computer discovered in a shipwreck off the Greek coast. For decades after its discovery in 1901, it was dismissed as an anomaly, too sophisticated for its supposed age of around 100 BCE. Only recently have we begun to understand that this intricate device could predict eclipses, track planetary movements, and calculate Olympic Games schedules with stunning accuracy. It suggests a level of technological sophistication that doesn't fit our neat timeline of scientific progress. These aren't just historical curiosities, they're reminders that human ingenuity has always been with us, sometimes flowering in unexpected places, sometimes forced underground by circumstances beyond its control. They suggest that our ancestors were far more capable, curious, and sophisticated than traditional narratives might have us believe. As we embark on this journey together, we'll discover that the phrase lost to science often means not truly lost, but simply overlooked, suppressed, or forgotten. Like archaeologists of knowledge, we'll brush away the dust of centuries to reveal the brilliant minds that have always been there, waiting patiently for someone to notice their contributions to our understanding of the world. The stories we're about to explore span continents and millennia. They include discoveries in astronomy that predated Galileo by centuries, medical insights that could have saved millions of lives if they hadn't been ignored, and technological innovations that disappeared into history only to be invented again, much later. But perhaps most importantly, these stories remind us that science is not just a collection of facts or formulas, it's a fundamentally human endeavor, driven by the same curiosity that makes you pause to watch a sunset or wonder about the stars. It's about the persistent itch to understand, the gentle rebellion of asking but why, and the quiet courage to look deeper when others are content with surface explanations. So settle in a little deeper. Let your breathing slow, and prepare to meet some of the most remarkable minds in human history. Minds that have been waiting in the shadows for their stories to be told again. Tonight, we're going to give them voice. Chapter 2. Setting the scenes. The great library burns, but knowledge finds a way. To understand how so much scientific knowledge became hidden or lost, we must first understand the fragile nature of preservation in the ancient world. Imagine, if you will, scrolls of papyrus and parchment as the hard drives of antiquity, delicate, susceptible to fire, flood, and the simple passage of time. Unlike our digital age where information can be copied infinitely, knowledge in the ancient world existed in single copies, or at best in a handful of hand-copied manuscripts. The burning of the Great Library of Alexandria has become a symbol of lost knowledge, though scholars now believe it was not destroyed in a single dramatic conflagration, but rather declined gradually over centuries due to funding cuts, political upheaval, and changing priorities. Yet this image of flames consuming scrolls serves as a powerful metaphor for how knowledge disappeared throughout history, sometimes dramatically, more often through simple neglect. But here's where our story takes an interesting turn. Even as libraries burned and empires fell, knowledge had a curious way of surviving. Like seeds that lie dormant in the desert until the rare rainfall allows them to bloom, scientific insights had a tendency to preserve themselves in unexpected ways and places. Consider the scholars of the Islamic Golden Age, roughly from the 8th to the 13th centuries. While Europe was experiencing what we somewhat unfairly call the Dark Ages, centers of learning flourished in Baghdad, Cordoba, Cairo, and other cities across the Islamic world. These scholars didn't just preserve the knowledge of ancient Greece and Rome, they expanded upon it, made new discoveries, and developed innovative techniques that wouldn't appear in European texts for centuries. The House of Wisdom in Baghdad, established in the early 9th century, was perhaps the greatest research institution of its time. Here, scholars translated works from Greek, Persian, Sanskrit, and other languages into Arabic, but translation was just the beginning. They engaged in original research, conducted experiments, and made observations that pushed the boundaries of human knowledge. Take the work of Al-Hazan, known in the Islamic world as Ibn al-Haytham, who lived from around 965 to 1040 CE. While European scholars were still largely accepting ancient authorities without question, Al-Hazan was developing what we now recognize as the scientific method, the systematic testing of hypotheses through experimentation and observation. His work on optics was so advanced that it wouldn't be matched in Europe until the time of Roger Bacon, some 2 centuries later. Yet for many years, Al-Hazan's contributions were largely unknown in the West, and when they were eventually discovered and translated, they were often attributed to European scholars or simply presented without acknowledgement of their true origins. This pattern, the slow, often uncredited transmission of knowledge from one culture to another, is one of the great themes of our story. The Mongol invasions of the 13th century dealt a devastating blow to many of these centers of learning. When Baghdad fell in 1258, contemporary accounts tell us that so many books were thrown into the Tigris River that its waters ran black with ink. The loss was catastrophic, yet even then, knowledge found ways to survive. Some scholars fled to other cities, carrying their wisdom with them. Others had already transmitted their discoveries to colleagues in distant lands. The ideas lived on, sometimes going underground for centuries before re-emerging in new forms. This pattern of preservation, loss, and rediscovery wasn't unique to the Islamic world. In medieval Europe, monasteries served as unlikely repositories of scientific knowledge. While we often think of medieval monks as focused solely on theological matters, many were accomplished astronomers, mathematicians, and natural philosophers. They preserved not just religious texts, but also works on medicine, astronomy, and natural history. But here's where the story becomes particularly poignant. Many of these monastic scholars were women whose contributions were systematically minimized or erased from the historical record. The abbess Hildegard of Bingen, who lived in the 12th century, was not only a mystic and composer, but also a skilled physician and naturalist, whose writings on medicine and the natural world were remarkably sophisticated for her time. Yet for centuries, her scientific work was overshadowed by focus on her mystical visions. Similarly, in medieval Islamic lands, women scholars made significant contributions to medicine, mathematics, and other fields, though their names and achievements were often omitted from later historical accounts. This systematic erasure of women's contributions to science is one of the most troubling patterns in our story of hidden knowledge. The Black Death of the 14th century dealt another blow to the preservation of knowledge. Entire scriptoriums, the rooms where manuscripts were copied by hand, were abandoned as their scribes fell victim to the plague. Countless texts that existed in only one or two copies simply vanished. And yet, even in the face of such catastrophic loss, some knowledge survived in the most unexpected places. Alchemical texts, for instance, were often preserved because they were thought to contain secrets of immortality or the ability to transform base metals into gold. While we now understand that much of alchemy was based on incorrect assumptions, these texts also contained sophisticated observations about chemical reactions in metallurgy. The search for the philosopher's stone led to discoveries about acids, alkalis, and chemical processes that would later contribute to the development of modern chemistry. Trade routes also played a crucial role in the transmission of knowledge. The Silk Road carried not just goods but ideas, techniques, and discoveries across vast distances. A mathematical concept developed in India might find its way to China, where it would be refined and combined with local insights before eventually reaching the Islamic world, and much later, Europe. This slow diffusion of knowledge meant that discoveries might be rediscovered multiple times in different places, with each culture adding its own insights and modifications. The printing press, invented in the mid-15th century, finally began to change this fragile ecosystem of knowledge preservation. For the first time, multiple copies of texts could be produced relatively quickly and cheaply, reducing the risk that a discovery would be completely lost if a single manuscript was destroyed. Yet even then, many works remained in manuscript form, accessible only to a small number of scholars. As we stand at the threshold of exploring these hidden discoveries, it's worth reflecting on what this historical context tells us about the nature of scientific progress. It's not a steady march forward, but rather a complex dance of discovery, preservation, loss, and rediscovery. Ideas emerge, go underground, and resurface in new forms. Knowledge crosses cultural and linguistic boundaries, often without recognition or attribution, and throughout it all, human curiosity persists, finding new ways to understand the world even when the old ways have been forgotten. The scholars we're about to meet weren't working in isolation. They were part of vast, often invisible networks of knowledge that stretched across continents and centuries. Their discoveries built upon the work of others, and in turn influenced scholars they would never meet. In understanding their stories, we begin to see science not as a collection of individual achievements, but as a collective human endeavor that transcends borders, languages, and epochs. So as we prepare to delve deeper into these hidden histories, remember that we're not just uncovering facts about the past, we're tracing the complex pathways by which human understanding has developed over millennia, and perhaps gaining insight into how knowledge continues to flow and evolve in our own time. Chapter 3. The First Mystery Circle. Forgotten Astronomers Who Mapped the Heavens. Let us begin our exploration with perhaps the most fundamental of human sciences, the observation of the heavens. Long before Copernicus shocked Europe with his heliocentric model, long before Galileo pointed his telescope skyward, there were observers who mapped the stars with extraordinary precision and developed sophisticated models of planetary motion. In the highlands of ancient Peru, sometime around 1450 CE, an Inca astronomer whose name has been lost to history made careful observations of the Pleiades star cluster. This wasn't casual stargazing. The Incas had developed a complex astronomical system that guided their agricultural cycles, religious ceremonies, and administrative decisions. They recognized that the apparent brightness of the Pleiades changed with atmospheric conditions, and they used these observations to predict weather patterns with remarkable accuracy. But their astronomy went deeper than weather prediction. The Incas understood concepts that European astronomy wouldn't formally recognize for centuries. They observed what we now call dark constellations, the dark patches between stars that form patterns when viewed against the bright band of the Milky Way. These dark constellations were integrated into a sophisticated cosmological system that linked earthly events with celestial phenomena. More remarkably, recent archaeological evidence suggests that some Inca sites were aligned not just with the sun and moon, but with specific stars whose positions would have been barely visible to the naked eye. This level of precision implies observational techniques and instruments that have been completely lost to us. When Spanish conquistadors arrived, they dismissed Inca astronomy as primitive superstition, and within a generation, centuries of accumulated knowledge had vanished. But the Incas were not unique in this respect. Half a world away in medieval India, astronomers were making observations and calculations of stunning sophistication. Brahmagupta, working in the 7th century, developed techniques for calculating the positions of planets that wouldn't be matched in Europe until the time of Kepler. He understood concepts like zero and negative numbers that were unknown in the West, and he used these mathematical tools to create astronomical models of remarkable precision. Perhaps even more extraordinary was the work of Aryabhata, who lived in the late 5th and early 6th centuries EE. Nearly 1,000 years before Copernicus, Aryabhata proposed that the Earth rotated on its axis, and that the apparent movement of the stars was due to this rotation rather than to the stars themselves moving around the Earth. He calculated the length of the solar year as 365.25868 days, just 3.4 minutes longer than the modern value. Aryabhata also understood that the moon shines by reflected sunlight and correctly explained lunar and solar eclipses. His astronomical calculations were so accurate that they continued to be used in India for over a millennium, yet his work remained virtually unknown in Europe until the 18th century, long after European astronomers had independently arrived at similar conclusions. These patterns of independent discovery and cultural isolation repeat throughout our story. In ancient China, astronomers were making detailed observations and keeping careful records at the same time their counterparts in other parts of the world were developing their own sophisticated systems. Chinese astronomers recorded supernovae, stellar explosions, as early as 185 CE, centuries before such phenomena were systematically observed in the West. The Chinese astronomer Shen Kuo, working in the 11th century, made the first known description of the magnetic declination of a compass, the fact that magnetic north differs from true north by an angle that varies with location. This discovery was crucial for navigation, yet it remained unknown in Europe until the 13th century, when it was independently rediscovered by European navigators. Chinese astronomers also developed sophisticated instruments for astronomical observation. The armillary sphere, a complex three-dimensional model of the celestial sphere, was perfected in China centuries before similar instruments appeared in Islamic or European astronomy. These instruments allowed Chinese astronomers to make observations of remarkable precision, tracking the movements of planets and predicting eclipses with accuracy that matched or exceeded contemporary Islamic astronomy. But perhaps the most poignant example of forgotten astronomical knowledge comes from ancient Egypt. The ancient Egyptians understood that the star Sirius, the brightest star in the night sky, had a companion star that was invisible to the naked eye. This knowledge was preserved in the oral traditions of the Dogon people of Mali, who maintained detailed descriptions of Sirius B, a white dwarf star that wasn't discovered by Western astronomy until 1862 and wasn't photographed until 1970. How did ancient peoples know about a star too faint to see without a telescope? Some scholars have suggested that ancient astronomers had access to optical instruments that have been lost to us. Others propose that the knowledge was passed down from an even earlier civilization with more advanced technology. Still others argue that careful observation over many generations might have allowed ancient astronomers to infer the existence of the companion star from slight variations in Sirius's motion. Whatever the explanation, the Dogon traditions preserve astronomical knowledge that shouldn't have been available to ancient observers. They describe the orbit of Sirius B around Sirius A with remarkable accuracy, including details about the orbital period and the dense nature of the companion star. This knowledge was dismissed as fantasy by early anthropologists, only to be vindicated by modern astrophysics. The story of ancient astronomical knowledge isn't just about individual discoveries, it's also about the systematic approaches these civilizations developed for understanding the cosmos. The Mayans, for instance, developed a calendar system of extraordinary sophistication that tracked multiple celestial cycles simultaneously. Their understanding of Venus's synodic period, the time it takes for Venus to return to the same position relative to Earth and the Sun, was accurate to within hours over a 500-year period. Mayan astronomers also tracked the precession of the equinoxes, a subtle wobble in Earth's rotation that causes the position of stars to shift slowly over thousands of years. They incorporated this knowledge into their long-count calendar, which was designed to track vast periods of time with precision that wouldn't be matched by European calendar systems until the modern era. But here's what makes these achievements even more remarkable. They were accomplished without the mathematical notation systems we take for granted. Mayan mathematics used a base 20 system and included the concept of zero, which wasn't adopted in European mathematics until much later. With these tools, Mayan astronomers could perform calculations involving vast numbers and long time periods, creating calendars and astronomical tables that remained accurate over millennia. The loss of this astronomical knowledge represents one of the great tragedies in the history of science. When Spanish conquistadors arrived in the Americas, they systematically destroyed Mayan codices, bark paper books, that contained centuries of accumulated astronomical observations and calculations. Of the thousands of codices that once existed, only 4 survive today. We can only imagine what astronomical insights were lost in those flames. Similar patterns of loss occurred throughout the world. The Library of Alexandria, which we mentioned earlier, was said to contain detailed astronomical observations going back centuries. When these records were lost, later astronomers had to start over, rebuilding knowledge that had already been accumulated by their predecessors. Yet even in the face of such losses, astronomical knowledge has shown a remarkable ability to survive and resurface. The Almagest of Ptolemy, compiled in the 2nd century CE, preserved Greek astronomical knowledge for over 1,000 years. Islamic astronomers translated, preserved and expanded upon this work, adding their own observations and insights. When these Islamic texts were eventually translated into Latin, they brought back to Europe astronomical knowledge that had been lost during the medieval period. This pattern of preservation, loss, and rediscovery continues to this day. Modern archaeoastronomy, the study of ancient astronomical knowledge, continues to uncover evidence of sophisticated observations and calculations made by cultures that had been dismissed as primitive. Stone circles, Ancient buildings and even cave paintings are being recognized as sophisticated astronomical instruments and records. The megalithic site of Nabta Playa in southern Egypt, for instance, contains stone arrangements that appear to be aligned with specific stars and constellations. Some of these alignments date back over 6,000 years, making them among the oldest known astronomical monuments. The sophistication of these alignments suggests that Neolithic peoples had a far more advanced understanding of astronomy than previously believed. As we reflect on these forgotten achievements in astronomy, we're reminded that the human desire to understand the cosmos is universal and timeless. Across cultures and throughout history, people have looked up at the night sky and sought to find patterns, meaning, and predictability in the movements of celestial objects. Their observations and insights, even when forgotten or suppressed, represent an unbroken chain of human curiosity that connects us to our earliest ancestors. The next time you look up at the stars, remember that you're participating in one of humanity's oldest and most persistent scientific endeavors. The light reaching your eyes tonight has traveled across vast distances of space and time, just as the knowledge of ancient astronomers has traveled across vast distances of culture and history to reach us today. In both cases, we're witnesses to something that transcends the boundaries of any single civilization or era, the eternal human quest to understand our place in the universe. Chapter 4. The main story block: hidden healers and suppressed medicine. As we settle deeper into our exploration of lost knowledge, let us turn our attention to perhaps the most immediately vital of human sciences, the art of healing. Here, in the quiet corners of medical history, we find some of the most extraordinary stories of discovery, suppression, and eventual vindication. These are tales of healers whose insights could have saved millions of lives had their knowledge not been dismissed, suppressed, or simply forgotten. Picture, if you will, a summer evening in Vienna, 1847. In the maternity ward of the city's general hospital, a young Hungarian physician named Ignaz Semmelweis is troubled by a disturbing pattern he's observed. Women giving birth in one section of the hospital are dying at rates 5 times higher than those in another section. The difference, he realizes, is that one ward is staffed by doctors who also perform autopsies, while the other is staffed by midwives who do not. Semmelweis hypothesizes that doctors are carrying cadaverous particles from the autopsy room to the maternity ward on their hands. He institutes a policy requiring all medical staff to wash their hands with chlorinated lime solutions before examining patients. Almost immediately, the death rate in the doctor-staffed ward drops to match that of the midwife-staffed ward. You might expect that such a dramatic and easily observable improvement would be welcomed by the medical establishment. Instead, Semmelweis's colleagues were offended by the suggestion that gentlemen's hands could be unclean. The idea that invisible particles could cause disease seemed absurd to physicians trained in the classical tradition. Semmelweis was ridiculed, ostracized, and eventually dismissed from his position. He spent the rest of his life trying to convince the medical world of the importance of hand hygiene, becoming increasingly desperate and bitter as his pleas were ignored. In 1865, he suffered a mental breakdown and was committed to an asylum, where he died of an infection, possibly sepsis, resulting from a beating by guards. The irony is almost unbearable. The man who discovered one of the most important principles of infection control died of an infection that proper hygiene might have prevented. It wasn't until the 1880s, when Louis Pasteur's germ theory became widely accepted, that Semmelweis's insights were vindicated. By then, countless women had died needlessly from puerperal fever, childbed fever, that could have been prevented by simple hand washing. Today, Semmelweis is recognized as a pioneer of antiseptic procedure, but his recognition came decades too late to save the lives his discovery could have protected. Semmelweis's story illustrates a pattern we see repeatedly in medical history: vital knowledge being rejected, not because it was wrong, but because it challenged established beliefs and threatened existing power structures. But his story also connects to a much longer tradition of medical knowledge that has been systematically suppressed or ignored. Long before Semmelweis, there were healers who understood concepts that wouldn't be formally accepted by academic medicine for centuries. In ancient Egypt, physicians were performing sophisticated surgical procedures, including trepanation, drilling holes in the skull to relieve pressure from head injuries. The Edwin Smith Papyrus, dating to around 1600 BCE, but copying material that may be over 1,000 years older, contains descriptions of surgical procedures and anatomical observations that demonstrate remarkable medical sophistication. But perhaps even more significant than these ancient Egyptian achievements was the medical knowledge preserved and developed by women healers throughout the medieval period. These women, often working outside the formal structures of academic medicine, developed sophisticated understanding of herbal remedies, anatomy, and disease treatment that was often superior to the theoretical knowledge taught in university medical schools. The Trotula texts, which we mentioned earlier, represent one of the most important collections of medieval medical knowledge. These texts, probably compiled by women practitioners in the medical school of Salerno in the 11th and 12th centuries, contain detailed information about gynecology, obstetrics, and general medicine. The knowledge they contain was remarkably advanced: descriptions of cesarean sections, understanding of the importance of diet and health, and sophisticated approaches to pain management during childbirth. Yet as universities began to formalize medical education and exclude women from formal practice, this knowledge was gradually appropriated, modified, and often degraded. Practical insights developed through centuries of observation and experience were replaced by theoretical frameworks based more on classical authority than empirical evidence. This pattern of suppression was particularly pronounced when it came to women's health. Female healers had developed sophisticated understanding of contraception, abortion, and childbirth that was often more effective than the treatments offered by male physicians. But as the Catholic Church gained influence over medical practice, much of this knowledge was suppressed as heretical or immoral. The witch trials of the 16th and 17th centuries dealt a devastating blow to traditional healing knowledge. Many of the women accused of witchcraft were actually skilled herbalists and healers whose knowledge of plants and healing practices made them valuable members of their communities. When these women were executed, their knowledge often died with them, leaving communities with less effective healing traditions. Barbara Ehrenreich and Deirdre English, in their seminal work Witches, Midwives, and Nurses, argue that the witch trials were in part an effort to eliminate competition for university-trained and exclusively male physicians. Whether or not this was deliberate, the effect was to replace practical, empirically based healing knowledge with theoretical approaches that were often less effective. But the suppression of medical knowledge wasn't limited to Europe or to women's medicine. Throughout the world, colonization led to the systematic devaluation and suppression of indigenous medical traditions. In the Americas, African traditional medicine, and Asian medical systems, colonial authorities dismissed sophisticated healing traditions as superstition or primitive magic. Consider, for instance, the case of cinchona bark, used by indigenous peoples of South America to treat fever for centuries before European colonization. When Spanish colonizers observed this practice, they initially dismissed it as indigenous superstition. It wasn't until the 1630s when the wife of a Spanish colonial administrator was reportedly cured of malaria by cinchona bark. Even then, the knowledge was appropriated without acknowledgement. Cinchona bark became known in Europe as Jesuit's bark or Countess's powder, with no reference to the indigenous peoples who had originally discovered and developed its use. The active compound, quinine, became one of the most important antimalarial drugs in European medicine, enabling European expansion into tropical regions. Yet the indigenous knowledge that made this possible was rarely acknowledged or compensated. Similar patterns occurred throughout the colonial world. Traditional Chinese medicine, Ayurvedic medicine from India, and indigenous healing traditions from Africa and the Americas all contained sophisticated understanding of human physiology and effective treatments for various conditions. But colonial medical authorities systematically dismissed these traditions as unscientific, even while secretly appropriating useful knowledge from them. The story of William Withering and Digital Liss provides another example of this pattern. In 1775, Withering, an English physician, encountered an elderly woman who was treating dropsy fluid retention with a herbal remedy. The remedy was remarkably effective, and Withering eventually identified the active ingredient as coming from the foxglove plant. He spent years studying the plant's effects and eventually introduced Digitalis to formal medical practice. Digitalis became one of the most important heart medications in medical history. Withering received full credit for its discovery. But the elderly woman who originally knew of the plant's properties, and the generations of traditional healers who had passed down this knowledge, received no recognition. Their contribution to medical knowledge was erased from the official record, remembered only in Withering's private notes. This pattern of appropriation and erasure extends to more recent times as well. Many of the pharmaceuticals that form the backbone of modern medicine were originally derived from traditional remedies. Aspirin came from willow bark, which had been used for pain relief for centuries. Morphine came from opium poppies, whose pain-relieving properties were well known in ancient medicine. Antibiotics like penicillin were preceded by traditional uses of moldy bread and other fermented materials to treat infections. In each case, traditional knowledge provided the foundation for scientific investigation, but the original sources of this knowledge were often forgotten or deliberately ignored in the official histories of medical discovery. This erasure wasn't just a matter of historical accuracy, it had real consequences for the development of medical knowledge and the recognition of diverse healing traditions. The suppression and loss of traditional medical knowledge also meant the loss of holistic approaches to health that might have prevented some of the problems that plague modern medicine. Traditional healing systems often emphasized prevention, lifestyle modification, the treatment of root causes rather than just symptoms. They recognized the interconnectedness of mental and physical health, and the importance of social and environmental factors in wellness. Modern medicine, in its focus on specific pathogens and discrete biological mechanisms, sometimes lost sight of these broader perspectives. Only recently has mainstream medicine begun to rediscover concepts like the importance of nutrition in health, the role of stress in disease, and the value of preventive approaches, insights that were central to many traditional healing systems. The story of scurvy provides a particularly striking example of how medical knowledge can be lost and rediscovered multiple times. Scurvy, caused by vitamin C deficiency, was a major problem for sailors on long voyages. By the 16th century, some ship surgeons had observed that citrus fruits could prevent and cure scurvy. Dutch sailors were routinely carrying sauerkraut and other preserved vegetables that prevented the disease. Yet this knowledge was repeatedly lost and rediscovered. Naval authorities would forget the importance of anti-scorbutic foods, sailors would die of scurvy, and then someone would rediscover the cure. It wasn't until James Linn's controlled trial in 1747, and the subsequent adoption of lemon juice by the British Navy, that the prevention of scurvy became standardized practice. Even then, the underlying mechanism, vitamin C deficiency, wasn't understood until the 20th century. The repeated loss and rediscovery of scurvy prevention illustrates how medical knowledge, even when empirically validated, can be forgotten if it's not properly systematized and transmitted. It also shows how institutional resistance to change can prevent the adoption of life-saving treatments. Perhaps nowhere is the pattern of suppressed medical knowledge more apparent than in the history of mental health treatment. For centuries, people with mental illness were treated as possessed by demons, morally corrupt, or simply incurable. Yet throughout this same period, there were healers who recognized mental illness as a medical condition and developed effective treatments. Avicenna, the great Islamic physician of the 10th and 11th centuries, wrote extensively about mental health, describing conditions we would now recognize as depression, anxiety, and other psychiatric disorders. He developed treatment approaches that emphasize the importance of environment, social relationships, and what we might now call therapy. His insights into the connection between mental and physical health were remarkably sophisticated, yet they remained largely unknown in European medicine until much later. Similarly, in many traditional cultures, shamans and traditional healers developed sophisticated approaches to mental health that recognized the importance of community, ritual, and symbolic healing. While these approaches were often dismissed by Western medicine as primitive superstition, Modern research in fields like narrative therapy and community mental health has begun to recognize their value. The systematic suppression of alternative medical knowledge continues to this day. Regulatory authorities in many countries make it difficult for traditional healers to practice, even when their treatments are effective. Research into alternative treatments is often underfunded, and positive results are sometimes dismissed or ignored by mainstream medical journals. At the same time, pharmaceutical companies spend billions of dollars investigating traditional remedies, seeking to isolate and patent active compounds. This process, sometimes called biopiracy, allows companies to profit from traditional knowledge while providing no benefit to the communities that originally developed and preserved this knowledge. Yet, despite centuries of suppression and appropriation, traditional medical knowledge continues to survive and contribute to human health. The World Health Organization now recognizes the importance of traditional medicine and supports research into traditional healing practices. Medical schools are beginning to teach about alternative approaches to health and healing, and patients are increasingly seeking out integrative approaches that combine the best of modern medicine with traditional healing wisdom. The story of suppressed medical knowledge reminds us that healing is both an art and a science, and that some of the most important insights come not from laboratories or clinical trials, but from careful observation of human suffering and the compassionate desire to relieve it. The healers we've met in this chapter, from Semmelweis to anonymous wise women to traditional practitioners around the world, shared a common commitment to reducing human suffering, even when their efforts were unrecognized or actively opposed. As we continue our journey through hidden scientific knowledge, we carry with us the reminder that some of the most important discoveries are made, not by those seeking glory or recognition, but by those who simply cannot bear to watch others suffer when they know of a better way. Their stories remind us that science, at its best, is driven not by abstract curiosity alone, but by love. Love for humanity, love for truth, and love for the possibility of a world with less pain and more healing. Chapter 5. The Mathematics That Disappeared and Reappeared. Let us now turn our attention to perhaps the most abstract yet fundamental of all sciences, mathematics. Here, in the realm of numbers, equations, and geometric proofs, we find some of the most remarkable stories of human intellectual achievement, discoveries so elegant and powerful that they seem to transcend the cultures that created them. Yet mathematics, like other forms of knowledge, has been subject to the same patterns of loss, suppression, and rediscovery that we've seen in astronomy and medicine. Picture a quiet monastery in medieval Ireland, perhaps sometime in the 8th century. A monk whose name has been lost to history is working by candlelight on a mathematical problem. He's not simply copying ancient texts, he's making original calculations, exploring number relationships that won't be formally recognized in European mathematics for another 5 centuries. His work is motivated not by abstract curiosity alone, but by practical needs, calculating dates for religious festivals, determining the proper proportions for architectural projects, or solving problems related to land measurement and taxation. This unnamed monk is just one of countless mathematicians whose contributions have been forgotten or minimized in standard historical accounts. Mathematics, perhaps more than any other science, has suffered from the peculiar myth that it develops in isolation from cultural and historical contexts. We tend to think of mathematical truths as eternal and universal, discovered rather than created. While there's some validity to this view, it has led to a profound underappreciation of how mathematical knowledge actually developed, often through the work of marginalized individuals and communities whose contributions were later attributed to others or forgotten entirely. Consider the case of zero, perhaps the most revolutionary concept in the history of mathematics. Most people, if asked, might guess that zero was invented by the Greeks or perhaps the Romans. In fact, the concept of zero, as both a placeholder and a number in its own right, was developed in India, probably sometime around the 5th century CE. The mathematician Brahmagupta, working in the 7th century, provided the first known rules for computing with zero, including the revolutionary insight that any number multiplied by zero equals zero. This might seem obvious to us now, but it represented a profound conceptual breakthrough. Earlier mathematical systems could represent the absence of quantity, but the idea of treating this absence as a number that could be manipulated algebraically was genuinely revolutionary. It enabled advances in algebra and calculation that would have been impossible otherwise. The concept of zero traveled slowly westward, carried by Islamic mathematicians who recognized its extraordinary utility. Muhammad al-Hafiz and Musa al-Khwarizmi, working in 9th century Baghdad, used zero in his algebraic calculations and helped transmit both the concept and Hindu-Arabic numerals to the Islamic world. The word algorithm itself derives from al-Khwarizmi's name, testament to his influence on mathematical thinking. Yet when zero finally reached Europe, probably through the work of Fibonacci in the 13th century, its origins in Indian mathematics were largely forgotten. For centuries, European texts referred to Arabic numerals and algebra, with little acknowledgement of the Indian origins of these concepts. It wasn't until much later that scholars began to trace these ideas back to their true sources. This pattern of cultural transmission and historical amnesia repeats throughout mathematical history. The theorem we know as the Pythagorean theorem, that in a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides, was known to Babylonian mathematicians over 1,000 years before Pythagoras was born. Clay tablets from the Old Babylonian period show sophisticated understanding of this relationship and its applications. Similarly, the mathematical concept we call Pascal's triangle, a triangular arrangement of numbers where each number is the sum of the two numbers directly above it, was known to Islamic mathematicians centuries before Pascal, and to Chinese mathematicians centuries before that. The Chinese mathematician Yang Hui described the triangle in 1261, calling it the diagram of old method for finding square and cubed roots. Yet in the West, it bears Pascal's name, reflecting our tendency to credit discoveries to the people who introduced them to European mathematics rather than their original discoverers. Perhaps no field of mathematics illustrates the problem of lost knowledge more clearly than algebra. We tend to think of algebra as beginning with European mathematicians like François Viet or René Descartes. In reality, sophisticated algebraic methods were being developed in many different cultures, often independently and often with remarkable elegance. The Islamic mathematician al-Khwarizmi, whom we mentioned earlier, wrote a treatise called Al-Jabr wal Muqabalah in the 9th century. The word al-Jabr gives us our word algebra, and al-Khwarizmi's work established many of the fundamental methods still taught in algebra classes today. But al-Khwarizmi wasn't working in isolation. He was building on earlier Indian and Greek work while also making original contributions. More remarkably, algebraic methods were being developed independently in other parts of the world as well. In ancient China, mathematicians developed sophisticated techniques for solving systems of linear equations that weren't known in the West until much later. The Chinese method of Gaussian elimination, a technique for solving systems of linear equations, was described in the Chinese mathematical text, the 9 chapters on the mathematical art, which dates to the Han Dynasty 206 BCE to 220 CE. This Chinese text contains mathematical insights that wouldn't appear in European mathematics for over a millennium. Chinese mathematicians understood negative numbers, worked with systems of linear equations, and developed approximation methods for extracting square roots. They even had a version of what we now call the binomial theorem, which allows for the expansion of expressions like a plus beth. But perhaps the most striking example of advanced Chinese mathematics is the work of Lu Xun in the 3rd century CE. Lu Xun calculated pi to 6 decimal places using a method that involved inscribed and circumscribed polygons with 12,288 sides. This level of precision wouldn't be matched in European mathematics until the 16th century, over 1,000 years later. The loss of Chinese mathematical knowledge to the West wasn't accidental. It reflected the limited cultural exchange between East and West during much of the medieval period. When European missionaries and merchants finally began to encounter Chinese mathematics in the 17th and 18th centuries, they were astonished by its sophistication. The Jesuit missionary Matteo Ricci, working in China in the late 16th and early 17th centuries, wrote admiringly of Chinese mathematical knowledge and helped facilitate some exchange between Chinese and European mathematical traditions. But by then, European mathematics had developed its own sophisticated methods, and there was little incentive to acknowledge that many European discoveries had been anticipated by Chinese mathematicians centuries earlier. The pattern of independent discovery and cultural isolation meant that mathematical insights were often developed multiple times in different cultures, with each culture claiming credit for discoveries that had been made elsewhere long before. This pattern extends to more recent times as well. The mathematician Srinivasa Ramanujan, working in isolation in early 20th century India, rediscovered many results that had already been proven by European mathematicians. But Ramanujan also discovered new theorems and identities that astonished European mathematicians when they finally encountered his work. His notebooks, filled with extraordinary mathematical insights, continue to yield new discoveries even today. Ramanujan's story illustrates another pattern in mathematical history: the role of intuition and insight in mathematical discovery. Many of Ramanujan's results were stated without proof. He seemed to intuit mathematical relationships that he couldn't always justify rigorously. This approach was initially dismissed by some European mathematicians, who valued rigorous proof above all else. Yet many of Ramanujan's intuitive insights have since been proven correct, suggesting that there are ways of understanding mathematical truth that don't always fit conventional academic approaches. The suppression of mathematical knowledge has sometimes been deliberate. In medieval Europe, advanced mathematical knowledge was sometimes viewed with suspicion by religious authorities. The use of Hindu-Arabic numerals was initially banned in some cities, partly because merchants could use them to conceal fraudulent calculations from officials who were familiar only with Roman numerals. The association of mathematics with Islamic culture also made it suspect in some Christian contexts. More systematically, the exclusion of women from formal education meant that women's mathematical contributions were often invisible or attributed to male colleagues. The case of Hypatia, the Alexandrian mathematician and philosopher who was murdered by a Christian mob in 415 CE, is well known. But there were many other women mathematicians whose contributions were minimized or forgotten. Sophie Germain, working in late 18th and early 19th century France, made important contributions to number theory and mathematical physics. But because women were excluded from the École Polytechnique and other mathematical institutions, Germain had to correspond with leading mathematicians under a male pseudonym. Even when her identity became known, her work was often marginalized or credited to her male correspondents. Emmy Noether, often considered the greatest woman mathematician in history, developed some of the most important theorems in abstract algebra and theoretical physics. Yet she struggled throughout her career to find academic positions, partly because of discrimination against women, and partly because of anti-Semitism. Her theorem connecting symmetries with conservation laws is fundamental to modern physics, yet it remained relatively unknown outside specialized circles for decades. The pattern of mathematical knowledge being lost and rediscovered extends to entire mathematical fields. Projective geometry, for instance, was known to ancient Greek mathematicians, but was largely forgotten during the medieval period. It was redeveloped in the Renaissance by artists who needed sophisticated techniques for representing three-dimensional objects on flat surfaces. The mathematical principles underlying perspective drawing led to important insights about the geometric properties of space and form. Similarly, the mathematical study of infinity was explored by ancient Indian mathematicians who recognized that some infinities could be larger than others, an insight that wouldn't be formalized in European mathematics until the work of Georg Cantor in the late 19th century. The Jain mathematicians of ancient India developed sophisticated concepts about infinite sets and transfinite numbers that anticipated some of the most advanced developments in modern set theory. The cyclical nature of mathematical knowledge, its tendency to be lost and rediscovered, suggests something profound about the nature of mathematical truth itself. Mathematical relationships seem to have an existence independent of the cultures that discover them. The same theorems and identities appear again and again in different times and places, suggesting that mathematical truth is genuinely universal, even if mathematical practice is culturally situated. Yet the specific ways in which mathematical ideas are expressed, understood, and applied are deeply influenced by cultural contexts. Chinese mathematics, with its emphasis on practical problem-solving and computational techniques, developed differently from Greek mathematics, with its focus on geometric proof and logical rigor. Islamic mathematics, building on both traditions while adding its own innovations, created yet another approach to mathematical thinking. The diversity of mathematical traditions reminds us that there's no single correct way to approach mathematical problems. Different cultures have developed different methods, different notations, and different ways of thinking about mathematical relationships. This diversity is a strength, not a weakness. It suggests that mathematical understanding can be enriched by exposure to different approaches and perspectives. Modern mathematics has begun to acknowledge this diversity more explicitly. Mathematical historians now work to trace the true origins of mathematical concepts, giving credit where it's due, rather than perpetuating myths about mathematical discovery. Cross-cultural studies of mathematics reveal the rich variety of ways in which different cultures have approached mathematical problems. At the same time, modern mathematics faces new challenges related to the preservation and transmission of knowledge. The increasing specialization of mathematical fields means that important results in one area may be unknown to specialists in other areas. The rapid pace of mathematical publication makes it difficult to keep track of all new developments, and the reliance on computer-assisted proofs raises questions about what it means to truly understand a mathematical result. As we reflect on the hidden history of mathematics, we're reminded that mathematical knowledge, like all human knowledge, is fragile and contingent. The theorems that seem so solid and eternal to us were discovered by specific individuals working in specific contexts, often overcoming significant obstacles and prejudices. Their insights could have been lost just as easily as they were preserved. The mathematicians we've met in this section, from anonymous Irish monks to Indian innovators to Chinese computational masters, remind us that mathematical discovery is a fundamentally human activity. It requires not just abstract reasoning, but also creativity, persistence, and often considerable courage. The next time you work with numbers, solve an equation, or think about geometric relationships, remember that you're participating in a tradition that spans cultures and millennia, built on the accumulated insights of countless individuals whose names and stories we may never know, but whose mathematical legacy continues to shape our understanding of the world. Chapter 6. The Alchemists' Secret Science. As our gentle exploration through forgotten knowledge continues, we arrive at perhaps the most misunderstood tradition in the history of science, alchemy. To modern ears, the word alchemy conjures images of bearded wizards hunched over bubbling cauldrons, frantically trying to turn lead into gold or concoct elixirs of immortality. This popular image isn't entirely wrong, but it misses the profound contributions that alchemical traditions made to our understanding of matter, chemistry, and the natural world. Picture, if you will, a workshop in medieval Baghdad, sometime in the 9th century. The air is thick with the smoke of various substances being heated in clay vessels. Glass tubes and retorts catch the flickering light of oil lamps, and the shelves are lined with jars containing powders, liquids, and crystals of every imaginable color. This is the laboratory of Jabir ibn Hayyan, known in the Latin West as Geber, a man whose contributions to chemistry were so significant that the word gibberish may derive from corrupted translations of his complex technical writings. Geber was not the stereotypical alchemist of popular imagination. He was a systematic experimenter who developed many of the fundamental techniques still used in chemistry today. He described processes for purification, distillation, crystallization, and sublimation. He was the first to prepare sulfuric acid, nitric acid, and aqua regia, the mixture of acids that can dissolve gold. His work on the classification of chemical substances laid groundwork that wouldn't be fully developed in European chemistry until centuries later. But Jabir's significance goes beyond his specific discoveries. He represented a fundamentally different approach to understanding matter, one that emphasized direct experimentation and observation over purely theoretical speculation. While European scholars were still largely relying on ancient authorities like Aristotle, Jabir was conducting controlled experiments, keeping detailed records and developing new theories based on empirical evidence. This experimental approach was central to alchemical practice throughout the Islamic world. Alchemists like al-Razi, known in the West as Rezis, continued and expanded upon Jabir's work, developing increasingly sophisticated understanding of chemical processes. Al-Razi classified substances into metals, vitriols, boraxes, salts, and stones, categories that reflected genuine chemical properties rather than purely theoretical distinctions. Al-Razi also made discoveries that wouldn't be formally recognized in European chemistry until much later. He was the first to describe sulfuric acid and alcohol in detail. He developed techniques for purifying metals and preparing pharmaceutical compounds. His medical writings, which integrated alchemical knowledge with clinical observation, were used as textbooks in European universities for centuries. But perhaps most importantly, these Islamic alchemists were developing what we might recognize as the scientific method. They emphasized the importance of reproducible experiments, careful measurement, and systematic observation. They kept detailed records of their procedures, allowing other alchemists to verify and build upon their work. This approach represented a revolutionary departure from the authority-based scholarship that dominated other fields of medieval learning. When alchemical knowledge began to filter into medieval Europe, it came through translations of Islamic texts. European scholars encountered not just specific techniques and discoveries, but an entire methodology for investigating the natural world. This methodology would prove to be one of alchemy's most important contributions to the development of modern science. The European tradition of alchemy that developed from these Islamic roots was more complex than popular stereotypes suggest. While the search for the philosopher's stone, the legendary substance that could transmute base metals into gold, was indeed central to alchemical thinking, this quest was embedded in sophisticated theories about the nature of matter and transformation. Alchemists believed that all metals shared a common, underlying nature and differed only in the proportions of certain fundamental principles. This wasn't entirely wrong. We now know that all elements are indeed composed of the same fundamental particles, protons, neutrons, and electrons, and that transmutation is possible, though it requires nuclear reactions rather than chemical processes. The alchemical theory of the four elements, earth, air, fire, and water, and the later theory of the three principles, sulfur, mercury, and salt, provided frameworks for understanding chemical reactions and material properties. While these theories were ultimately incorrect in their specifics, they represented serious attempts to explain observed phenomena and guide experimental investigation. The search for the elixir of life, a substance that could cure all diseases and grant immortality, led alchemists to make important discoveries in medicine and pharmacology. Paracelsus, the 16th century physician-alchemist, revolutionized medical practice by applying alchemical principles to the preparation of medicines. He was among the first to use chemical compounds rather than just herbal remedies in medical treatment. Paracelsus also introduced the concept of chemical dosage, the idea that the difference between medicine and poison often lies in the quantity administered. His famous maxim, "The dose makes the poison," remains a fundamental principle of pharmacology. His work on the chemical treatment of diseases laid important groundwork for the development of modern pharmaceutical chemistry. But alchemy wasn't just about practical discoveries. It also preserved and transmitted important philosophical ideas about the relationship between mind and matter, the observer and the observed. Alchemical texts often describe psychological and spiritual transformations alongside material ones, recognizing that the investigator's state of mind could influence both the conduct and interpretation of experiments. This psychological dimension of alchemy has often been dismissed as mystical nonsense, but it actually reflected sophisticated insights about the role of subjectivity in scientific investigation. Modern philosophy of science has come to recognize that the observer's expectations, beliefs, and mental framework can indeed influence experimental results, especially in complex systems. The alchemists' emphasis on the inner transformation of the experimenter anticipated some of these insights. The alchemical tradition also preserved important knowledge about metallurgy, mining, and materials science. Alchemical texts contain detailed descriptions of techniques for extracting metals from ores, purifying metals, creating alloys, and preparing various chemical compounds. Much of this knowledge was essential to early industrial development, though its alchemical origins were often forgotten or deliberately obscured. The famous alchemist George Starkey, working in 17th century New England, developed techniques for producing pharmaceutical compounds that were more effective than anything available in conventional medicine of his time. His processes for preparing antimony-based medicines were so successful that they continued to be used well into the 18th century, long after the theoretical framework that guided their development had been abandoned. Similarly, the mining techniques described in alchemical texts like Georgius Agricola's Debra Metallica were based on centuries of accumulated practical knowledge. Alchemists had developed sophisticated understanding of how different metals behaved under various conditions, how to separate valuable metals from ore, and how to create new materials with desired properties. But as the scientific revolution of the 17th and 18th centuries gained momentum, alchemy began to be seen as an obstacle to the development of rational chemistry rather than its foundation. The theoretical frameworks of alchemy, with their emphasis on hidden correspondences and symbolic relationships, seemed inconsistent with the mechanical philosophy that was transforming natural philosophy. Robert Boyle, often considered one of the founders of modern chemistry, explicitly rejected alchemical theories while building upon alchemical practices. His famous work, The Sceptical Symist, criticized traditional alchemical theory while using experimental techniques developed by alchemists. This selective appropriation of alchemical knowledge, taking the practical methods while discarding the theoretical framework, became a common pattern. Antoine Lavoisier, whose work on combustion and the conservation of mass revolutionized chemistry in the late 18th century, similarly built upon alchemical experimental techniques while rejecting alchemical theory. His careful quantitative methods and systematic approach to chemical analysis were refinements of approaches originally developed by Islamic alchemists centuries earlier. The irony is that this rejection of alchemy often involved forgetting valuable insights along with discredited theories. The alchemical emphasis on the unity of nature, the interconnectedness of different phenomena, and the importance of process and transformation contained insights that wouldn't be fully appreciated again until the development of systems thinking in the 20th century. Modern chemistry has also had to rediscover some specific techniques that were known to alchemists but forgotten during the transition to modern scientific methods. The preparation of colloidal metals, for instance, was well known to medieval alchemists, who created ruby-colored gold colloids and other metallic suspensions. These techniques were lost and had to be redeveloped in the 19th century. Similarly, alchemists knew how to prepare various forms of carbon, including what we now recognize as forms of activated carbon, that had special properties for purification and adsorption. Some of these techniques weren't fully understood by modern chemistry until the development of surface chemistry and materials science in the 20th century. The alchemical tradition also preserved important knowledge about glass making, ceramic preparation, and the working of various materials. The beautiful colored glasses found in medieval churches often incorporated techniques developed by alchemists. The preparation of pigments, dyes, and other colored materials relied heavily on alchemical knowledge. Perhaps most importantly, alchemy provided a bridge between the abstract theoretical knowledge of ancient philosophy and the practical experimental approach of modern science. Alchemists were among the first to systematically investigate the properties of matter through hands-on experimentation. They developed many of the basic techniques of laboratory chemistry and established the tradition of learning about nature through direct manipulation and observation. The workshop of an alchemist, with its furnaces, distillation apparatus, and chemical reagents, was the direct ancestor of the modern chemistry laboratory. The methods alchemists developed for heating, cooling, mixing, separating, and analyzing substances provided the foundation for all subsequent developments in chemical technique. But beyond these practical contributions, alchemy represented something deeper, a recognition that understanding nature requires not just abstract theorizing, but patient, careful, repeated encounters with the material world. The alchemists' long hours spent observing chemical reactions, noting subtle changes and refining techniques represented a commitment to empirical investigation that was revolutionary for its time. The secrecy that surrounded alchemical practice, often seen as evidence of charlatanism or delusion, actually served important functions. In societies where innovation was often viewed with suspicion, and where powerful authorities might suppress threatening ideas, secrecy protected both the knowledge itself and those who preserved it. The complex symbolic language of alchemical texts served both to preserve knowledge and to limit access to it. This secrecy also fostered the development of close master-student relationships that were essential for transmitting complex practical knowledge. Unlike purely theoretical subjects that could be learned from books, alchemical practice required hands-on training, careful observation of subtle phenomena, and the development of practical skills that could only be acquired through direct experience. As we reflect on the hidden contributions of alchemy to modern science, we're reminded that the boundary between science and non-science is more fluid and historically contingent than we might expect. Ideas and practices that seem obviously scientific to us now were once embedded in theoretical frameworks that we now reject. And theoretical frameworks that we now dismiss as unscientific sometimes contained insights and methods that contributed to genuine scientific progress. The alchemists' quest to transform base metals into gold may have been impossible, but their investigations along the way led to genuine discoveries about the nature of matter and chemical change. Their search for universal medicines may have been overly ambitious, but it led to important advances in pharmacology and medical chemistry. Their belief in the unity of all natural phenomena may have been philosophically controversial, but it encouraged a systematic, experimental approach to investigating nature. The next time you see a chemistry laboratory, with its careful procedures, precise measurements, and systematic approach to investigation, remember that you're looking at the direct descendant of those medieval workshops where alchemists first began to unlock the secrets of matter through patient experimentation. Their quest for transformation, both material and spiritual, continues in every scientist who seeks to understand and change the world through careful observation and innovative thinking. The alchemists may not have found the philosopher's stone, but they left us something even more valuable: the knowledge that nature's secrets can be unlocked through careful observation, systematic experimentation, and the patient willingness to be surprised by what we discover. In a very real sense, every modern laboratory is still an alchemical workshop, still engaged in the ancient quest to understand and transform the material world.